But anyway, we have so we are going usually a little bit higher pace than usual, right? So we originally, I think the book were designed for 14 lectures, so like 2 lectures per week. Oh, sorry, two weeks per chapter or something. But now we have to go a little bit faster, and probably last couple of chapter will go a little bit faster, like a 1 week per chapter, right? So today we'll try to talk a little bit about chapter 7. That's sort of the applications, right? And so after all these days, right? Last 10 years, it's in the sense that the deep networks or the artificial intelligence is sort of driven by practice, right? Lots of applications. It's like, very, very, diverse, very dynamic, right? All types of, for all kinds of real world data, images, text, videos, 3D and audios and all the things, right? So it's like real world data. Now, this course, we have spent the whole semester study, how do we learn the structure of those real world data? And now, how do we connect to practice? We talk about the concept, what we're trying to, behind intelligence, what it's trying to do, the concepts, right? The principles behind it. Also, we talk about the framework, the computational framework, right? The architecture, what it's trying to do, right? Now, the theory behind it, even. Now the question is, can we actually connect to real practice? That's what, the theory will be useless. Any theory will be useless if it cannot really help to, first, explain the practice. Second, help to guide the practice, right? And even tell what the future practice will be, right? That's actually the main purpose. So today we'll try to go through, depends on how much time we have, right? We have to go through a few of the representative applications, right? So some of them you're probably familiar, DNO, MAE, and RAE, and some of the things. They all have something to do with learner representations. And we're primarily because of the interest of time, we don't have much, and we'll talk about primarily using images, right? Learn representation for images as example. I mean, in the book, there's also text. Probably in the future, we'll also add the 3D motion and other things, and also motion data, 3D data, objects, and so on, right? But here we are using the images as a representative, right? So one couple of administrative matters. So there's a homework has been distributed last week, as I understand. So we'll be doing about 1 week, some of the related to your assignment, right? So please synchronize that with the TA. If you have any questions, get to the TA and get to me, right? And also, I believe most of you are working on your final project. I think we're still scheduling maybe likely the second week of December. After, I think the first week is like kind of the reading week, preparation week. The second week we'll try to schedule some sessions that you can make your final presentation. Likely towards the end of the second week of December, your final report should be due, okay? It's kind of, so you probably just shy of 1 month for your final project, okay? And get everything ready. So that's your deadline, right? Towards the end of the second week, that's your deadline, okay? Besides your usual other deadlines. All right, so, as I said, right, last week, right? When we study something, a subject, we try to read a book, right? Study a subject. First thing is that we 把书读厚, right? I said before. Make the book feels like thick, very thick. Why? We wanted to see how this subject related to everything we know so far, historically, and also in all the related fields. What all the ideas has been developed around the subject we try to understand, okay? This is your responsibility, guys. This is your duty. This is scholarship. If you don't do that, right? Hear me out, right? Your life will not achieve anything significantly, okay? Trust me. Right? So this is a part of things to understand how all the related. This is part of the process of learning. Truly understand what's going on, what has gone, what has been done before, how things are related in different fields, okay? In mathematics, physics, right? In signal processing, in computer science, in information theory, in control, in optimization. Right? So many people have thought about similar problems, right? What have they thought about? What are the ideas? How they relies on each other? Right? You have to understand that thought process, right? And truly understand, right, what has been understood, right? What has been done. And then the second stage is try to do ball, right? Then maybe turns out everybody's doing the same thing, right? Remember, all roads lead to Rome, right? Interest in science, mathematics. In fact, what do we do? Machine intelligence. Maybe intelligence is all about something very, very unified. They're just manifestations, right? Everybody work on different pieces. 盲人摸象, right? Everybody touch different pieces of the, right? Or 只见树木不见森林. Everybody see a little bit piece of something commonly interested. Right? So this should be a mental picture. I mean, at least we believe our best understanding so far. If you forget everything, right, try to remember this mental picture. In fact, it turns out probably this is elephant, right? Or probably all the fields, everything, people actually just study a different part of it. Today we'll give you a little feeling about it, right? So we are interested in some real-world data in very high-dimensional spaces. But first, what we wanted to know, we want to get a hold of what the heck that distribution is, and likely to transform it to some structural representation, right? Maybe it's linear, right? In a very high-dimensional spaces, then goes through a compression, goes through a lossy compression, goes through a deformation, right? Or self-auto-regression, removing the nonlinearity as noise, gradually linearizes, maximize the information gain, reduce the coding rate, right? Hence, you get a better structural representation. This is really the process, right? Really reduction, information gain, they're just different measures. They're just measures, right? And they're trying to do what? Group, cluster, contract what is similar, contrast, separate, segment what is dissimilar, right? This is really what's the concept behind it. So that you end up with a very structured representation, linear, incoherent, right? And you can specify and so on and so forth. Now, the second thing is that once you have this representation, we're trying to make sure this is kind of auto-encoding, right? From the data and map to the representation be able to go back, right? So that this representation is what? Consistent or self-consistent, okay? Structured, consistent, and self-consistent. Now, once we get hold of this feature, right? We have this feature. By the way, don't think that you have Z, you have everything. You don't, because this Z is also in some space. This structure, this linear structure, is also in some high-dimensional spaces. You also want to get hold of it, be able to access it, be able to sample from it. Remember we talked about it, right? Even the structure is so simple, it's only like have one subspace. You still have to get hold of it. Have to learn that basis for that subspaces, right? Go using solve a PCA problem. Start from random vector, do power iteration to get hold of that subspace, right? Or if this happens to be a mixture of orthogonal subspaces, you learn the dictionary to orthogonalize, to sparsify. You learn a sparsifying dictionary so that you can go from here to decode, right? Or more generally, maybe this is just a bunch of low-dimensional subspaces. Probably almost incoherent, but I don't really know. I cannot guarantee they're orthogonal yet, right? Then I maybe have to have a more general process, treat it slightly as something general, although structured. I should have a way to access, to sample those subspaces and decode it to X. Clear? You have to be able to go from, be able to access this red dots or green dot subspace, then decode it back to X. So this is really the mental picture. To learn some structural representation, also be able to access it. And you can call this many different things, right? This is your memory, basically. You also be able to very quickly access it and use it to predict X, what's in the world. Given that this Z is rather consistent or self-consistent with observation X, right? You have auto-encoding to encode and decode. Okay, so this is actually the mental picture. What's going on the left? Now, the rest, this is the objective. This is what you really want, right? Now, the rest is how do I do it? Right? How to learn such a mapping, auto-encoding? How do I go for general nonlinear structure, low-dimensional structure, to such a highly structured one? Minimizing coding rate reduction. That alone, right? Do it in the incremental way. Unroll the optimization algorithm to optimize this object function. Give you the architecture. Give you the Bredoon-like or Crate-like, right? They're basically doing autoregression, right? We talk about this. Using autoregression to compute the residual and get rid of that. Remove the nonlinearity as noise, right? And also about this, we know how to do this in general, right? If we have such a target distribution, has a lot of data on it, we know the diffusion, denoising can be a general process to get hold of those samples on those structures, right? But today we'll talk about, but this is no longer, if this representation is arbitrary, unlike this one, right? This actually has good structure. Hence, this denoiser may have very good structure, may be very different from a generic denoiser. A denoiser for generic distribution, right? This guy may have very good structure. This guy may have a very good property. Right? For generic denoising process, it might take a long time to converge to that. But like PCA, right? If it's a linear structure, I have very, very fast. This process can be very, very efficient, very access. So this is basically the mental picture, right? Now, in terms of detail, what he's really doing is illustrated on the right side, right? This is actually allows you to deform the distribution, linearize it, push those data along, make them linear, gradually linear. And once this default denoising processes go from the whole space, try to contract, try to actually converge through a denoising or whatever you call it, denoising or compression process to actually be able to get to the ROMs, right? Get the structure. So this is actually I think the mental picture, right? Why we learn a representation. Why the world deep? The deep come from do this step by step in an unrolled optimization pattern. You do this iterative optimization, right? So the deep layer, the layers just realizing those incremental operators. Okay, now let's get to the more detail, right? Now, so this is elephant, right? But historically, people probably didn't know this, right? They work on different pieces, actually, right? Almost everything you heard so far, all this, right? It's about learning one piece out of this. The cut of the problem in this big gigantic picture, let's just work on maybe one piece. All right? And then they give a name. Right? And actually, sometimes they give multiple names to the same thing, right? Just one piece. Right? Every different method. For example, forget about autoencoding. What about just learn something from X to Z? That's just one tiny piece, right? That's actually exactly what the Dino, those things do, right? These days you heard about, you know, everybody use the world model, Yanacon or Meta, they do Dino. This is still property. Clip use it, everybody use it, you know, right? RE use it, right? And Sora use it, everybody use it, right? And so you learn some kind of a representation from this is images, patches, and you try to learn some features, right? using contractive learning, right? This is what you heard. Basically, it's just trying to learn this one segment from X to Z. It does not even try to make sure this is autoencoding yet, okay? Just some heuristic. They don't even understand the big picture, but this is something they do, they can do, right? They try to do. And how do I learn such a mapping? At least the Z is somehow good, right? Actually, to be honest, they don't even know what it's good for, right? Maybe Z is somehow capture a lot of good properties of X, does not collapse. Maybe encode a lot of patterns, right? Or invariant to different things, right? For example, different image, different rotation, different shifting, maybe X maybe mapping to the same feature, and so on. Hence, it's good for classification, for recognition, for segmentation, for some task, right? They try to learn a representation so that it's at least good for some understream tasks, right? So that's a measure how good Z is, right? Measured by the tasks, not something intrinsic, okay? Not something objective. Well, there's many ways, right? You're using contrastive learning, enforcing invariant, Sinclair, and Dino, and MAE. I bought Dino version 2 is a combination of all this. Right, also, we have seen something before, right? You can also, XZZ also go back to X. So MAE is actually autoencoding. Regardless, we're still looking at this part, right? X to Z part, okay? Still one tiny piece, right? Either just do this open end. We call this open loop. If you only learn F, right? This is an open loop end-to-end training. Or you do X to Z, Z back to X. We call it autoencoding, right? MAE will be one of those. Or you do X to Z, Z to X, X to back to Z, Z hat. We call it a closed loop. We talked about this before, right? There's just different way to make sure, right, the learned Z has some property, good structures, right? Optimizing different kind of objective function loss and so on, right? Also, you notice that when you do this, you don't need anything else. You don't need to segment X, classify X at all. It's just a set of data, right? The learning try to be unsupervised or self-supervised. Just try to learn something feature depends on X. Right? It's not yet train this for some specific task like a classification. Right? This is people call it unsupervised or supervised. But actually, personally, I don't want to separate them. I think supervised, unsupervised, self-supervised, they're all the same. Just depends on how much information you have about X. Right? If your purpose is about learning the distribution of X, it doesn't really matter. It's supervised, unsupervised. You just use all the information you have about X, right? Supervised setting just give you a little bit more information about X. Allows you to group better, cluster better, compress better. That's it, right? Easier to compress, cluster, right? So hence, those are the different settings, right? So today we'll talk a little bit about what people normally do this open. There are practical, see conceptually, right? Conceptually we talked about before. Conceptually we wanted this X to Z, Z to X to be autoencoding. Or even better, we want a self-consistency, right? But at least computationally, that you might pay a price, right? Be able to enforce autoencoding or enforce closed loop, you may have to pay a price. Computationally, it's more expensive to do that. Hence, these days, people try to strive for scalability, right? They want to scale this up. Maybe such an open loop system is easier to train, okay? And it's easier to engineer. So that's what the people do these days, okay? The choice is not conceptual. The choice is very practical. So I want you to think about it, right? After this course, don't confuse those things. Conceptually, what's the right thing to do versus practically, what is the choice? What is the choice for the time being? Those are very two different things. Okay? 不要让别人忽悠你啊. Is something is actually for a practical choice. Think, oh, this is it. This is the only way of doing it. This is the best way of doing it. No, don't ever get confused for that, right? Whatever being implemented right now, maybe just a lot of the reason is just being practical, okay? So that it can scale better. Now, so how do we learn such an F in an open loop setting? Right. Suppose we're not doing this auto loop. We're not doing the auto encoding yet. We just do this open. What can we use? to learn such a F. What do we want this F to be? Right? This is really what the behind this unsupervised, self-supervised learning is all about, right? For example, for images, of course, we want maybe different to be invariant to certain transformations, right? Because we want a Z, right? Give me an X, right? Everything related to dog, I want it to be maybe in the hidden space, the representation of all those different instances, different cropping, different color, noise, blocked, partially, all sort of map into a feature space related to close to dog. Okay, the feature should be similar. So this is called augmentation, right? People do this for training neural networks anyway, to do classification and so on. So basically, this is implicit says, try to make sure the feature Z you learned focus on the part common for all the images. Try to rule out irrelevant to the content you try to learn. Okay? Z only keeps what's relevant to the content you care. Right? So this is actually the right. But there's a problem though, right? If you want different variant differences, different representation, different instances, right? Different cropping, different augmentation, all mapped to the same. But then there's a trivial solution, right? You end up with map all images to a common vector. Then all the invariants, all the shift version map to the same thing. Right? 这些人讨厌，对不对？把所有的 cats, dogs, all map to the same features. Then doesn't matter. It's invariant. So there's a trivial invariant representation. Right? So you don't want that. You also want the Z to be informative. Remember the notion of information gain. 对吧? You also want what's similar, what should be similar, close. You want what's dissimilar to be separate. Right? 我们讲过无穷多次了, right? That's basically every learning criteria is actually trying to do this. You contract what is similar. You contrast what is dissimilar. That's exactly the contrastive learning is trying to do, right? People now, then maybe dogs and cats. This is a negative example for X. Or the different version of X are the positive example, right? They all should map to something similar, okay? All those images like this should be matched to some feature Z. But for dogs, should map to a feature Z, which is far from the feature Z for cats. Okay, this is very heuristically, as I said, right? It was very heuristic thinking. Okay, but now we know much better. How do we measure, right? Now you guys know much better than DFFA, right? Than those guys, right? That's what the people do. The practitioner, they play with intuition, they play with these heuristics, because they don't have the theory, they don't have the principle. They don't know how to do things objectively, okay? But the intuition might be right, right? Hence they come up with all kinds of weird things, right? Similar things, for example, this is what they come up with. Those features should be similar. The negative ones should be different, right? He Kaiming also played with this, right? At one time was so excited, oh, contrastive learning is everything, 对不对？现在还有人做这个吗？没有了，对不对？ I think it's about 2017-18年, right? The 2018. Then he was doing this MAE, contrastive learning, all the things, right? And I visited Yang Kun's office. That's all he talked about. He said, contrastive learning, that's it. That's the end of the world, right? Contrastive learning, right? Kaiming wrote a paper, spent 1,000 GPUs on it, learn some feature. Yes, did a little bit better than before, than clustering, classification, recognition, right? And everybody talk about it, right? The train object like this, everybody talk about the contrastive learning. That's it. It's like the end of the world, the last wagon, right? Right? We are marching to general intelligence, right? With this, right? You just learn for billions of images, you're done, okay? We recognize all the computer vision is solved, okay? By that time. That's it. That's the sentiment. I'm not joking. I'm not exaggerating, okay? That's literally the whole community think. This is it. This is the end of the world, okay? Right? That's how, strange the world can be these days, right? Something a little bit come out, a little bit better than before, they think, this is it. Now we know, right? This is far from it, right? This is far from anything, right? And then they jump to then Meta develop a team, right? Because of contrastive learning, right? They actually build a team, which is, I heard probably somewhere between, 30, 40 people, engineers for several years, try to engineer a system, right? To implement this kind of contrastive learning. And also contrastive learning is also, it's difficult because you actually need the negative examples, right? There's all kinds of tricks to, to create you need both positive and negative examples, right? But the negative example sometimes can come at a price, right? You still need at least some label, right? Some notion that the images are different, right? But when you train this at a very massive scale, this may not be that easily come by, okay? Sometimes even you can get positive example into the negative example, right? You can contaminate your data, right? So those relies on very good labels. What is different, what is not different, okay? So hence you train all the images in the world. It's very expensive to label those, to contrast those, right? So this is also created some engineering problem. Hence people try to, okay, how can we still learn, right, features for data that augmented data should match to similar features, but not have don't have too much contrastive samples, don't have too many negative examples, right? So they actually come up with this kind of teacher-student network, right? This is kind of DINO, very, very interesting. Try to make sure, right, to avoid, remember, if you don't have negative example, you cannot contrast. Hence your feature likely get all converged to the same darn thing, right, collapse. So there's a tendency to collapse. So how do you avoid the learned feature to be not to collapse? When you train this feature mapping F at a very large scale, it's a lots and lots of engineer, okay? There's a very large pipeline, different teachers, centering, softmask, stop, gradient, and all this. I don't know how to come up with, okay? But I heard this, they have a lot of resource to do this. And the sample, again, for each image is sample some global view and local view. Basically, same image. Those images are, you can think about the local view are just the augmentation of each sample, right? You try to map all those augmentation into the same picture, right? For teachers network, and you update them slightly differently, and so on. Right, you have to center them, you have to scale them. You can see there's all kinds of weird tricks, right, to make sure that this pipeline does not collapse, right? Centering, temperature, scaling, and so on, right? So let's try to train such a teacher-student network so they can train on billions of images to learn kind of feature space that's spread it out, right? But still, cropped image somehow gets mapped. So feature Z is a kind of invariant to all the cropping augmentation, but yet different image tends to spread it out. This feature space seems to be not collapsing. Okay. Right. So as I said, it's very empirical, requires very careful balance several components to avoid collapse. Stop grading operation between this teacher-student network, momentum encoder, the updates has to be very weird, moving average, temperature scaling, right? Different temperature parameter for the student-teacher network, control the sharpness of the outcome of the distribution. Each one has to match to try to emulate some distribution, a posterior distribution. And the centering of teacher output is centered by subtracting rounding mean. Anyway, there's all kinds of tricks. People come up with try and error. Somehow they be able to train this at a massive scale, right? As you can see, right? If you don't do this, if you don't do sharpening, you don't do centering, you have to put this in the right ingredients so that the training will not collapse. Okay, otherwise they just collapse. All right. It's a lot of engineering. It's like 20 or 30 different hyperparameters. People basically try to engineer systems, right? And then actually the DINO, at least for now, if you do this carefully, right, people still don't quite know what they're optimizing. Yes, they try to cluster what's supposed to be from the same image. Try to make sure, features from different image somehow spread it. Okay, that's it. They don't even know what they're optimizing. through engineering. But after training, it turns out doing this carefully, the Dino actually does give very good, reasonably good representation, right? Then you can use it for one shot. As long as you train this, the self is learned, you can do reasonably good classification performance. I think this is on image on ImageNet. You can get close to 70% one-shot classification. Pretty decent, right? And but we don't know. I mean, this is trained on all the many images, billions of images, right? We don't know if it contains the ImageNet or not, but at least they don't have the label. Okay, maybe they have seen the images, similar images, right? But this is, once you train this in a very unsupervised, self-supervised way, you do this on some of the data set which has class labels, does a decent job, okay, up to 70s. But this is already reasonably impressive because even for supervised learning, probably ImageNet with a network is about 80, right, 80-some%. Now the questions. Can we simplify Dino? Right. It's trying to do this through a purely empirical, right? You can see the system is extremely complicated, by the way. We'll see the vision 2, okay, what it looks like, okay? You'll see in a second what the vision 2 looks like. It's even more scarier, right? Right. But now we know the big picture. Now you guys know the concept, what we're supposed to do, right? The engineers don't. They play with the very intuitive notion of contrast or contract, okay? And even the measure are very heuristic, right? Map the feature, right? To some target distribution, Gaussian or isotropic, right? Though that's what the Yang and Kung talk about these days, right? Recent paper is about, right? Learn, without heuristic, actually has a lot of heuristics, right? So even the say paper says, the title says that the without heuristic actually has a lot of heuristic, right? And so the point is that, how do we learn? Now we know the purpose of learning some feature is really trying to make what's similar into a linear clustered, right? And what's different to be incoherent linear structure, right? Hence, we want to learn this autoencoding. We also want our encoding to be almost informative, very informative, right? Almost autoencoding. Yes, this can be lossy, but don't lose too much, right? Be able to recover X hat is close. We'll see how to measure this, right? In general, this is hard to measure, but in some cases, yes, we can, if we can pay the price. And also, of course, we want Z to be good, right? We have learned plenty of measures, right? How to measure Z. We want what's similar to be together, compressed, linear. We want what's different to be incoherent, separate, right? Expand. Right? We know that. Can we play with this? Right? For example, but keep here, right? We don't have a very good measure, right? Here we only care about in the Dino case. Remember, we're just doing in the open end, right? We're not decoding. We're not learning a decoder. So we only have this guy, right? We don't have a decoder here, Dino, right? So we have to come up with some, maybe the distance, just imagine we have decoded image. Those decoded image needs to have very similar features. Features should be similar. This is exactly what is a decoded image when you do not have a decoder. 大家能想象吗? I want to learn X to Z, right? But I don't have a decoder Z to X hat. What is a candidate for X hat? It can produce Z hat. What is Z hat? You can produce a hat. 我们刚刚已经讲过了，对不对? You don't have Z to X, right? But it can produce X hat, very similar to X. Just augmentation, 对不对? Because you already assume this guy is supposed to, all the X, similar X should map to similar Z. in its neighborhood. You know what neighborhood should look like, right? Those are precisely should contain images, are augmented, should be able to, if they were decoded correctly, right? If you had a G, those X should be very much similar to the augmented version of X. Should be similar to X, maybe differ by some rotation, translation, and scale, so on, right? So you do have this guy, which generated from X. Then those feature goes through the same feature. Those Z hat and Z should be similar. Okay, that's it. This is exactly the contractive learning part. Try to make sure Z for all the augmented instance to be similar, right? 所以这一项实际上我们已经有了，在这个前面的这个 Dino 里面 ，it's exactly using this. Okay, even you do not have decoding. 所以你现在知道吧 ？Augmented image is a decoding, a form of a decoding without the decoder. 明白吗？所以 now once you have those concepts, those all the things are very easy to explain, right? You're actually doing something equivalent to as if you already have a decoder. You can create those samples. Now, what about RZ? Remember, RZ is just all the set should not collapse, right? Actually, billions of images, they map to Z. Billions of X map to Z. Doesn't really matter. That whole set cannot collapse. Better expanded, right? So this is the Z, the similar part, right? So different coding. Teachers, so this is actually for the distance, right? The teacher student should be similar, and also augmented picture should be similar, right? That's very, very simple. What about Z? Whole set. We actually know how to do it, right? Just have all the Z's for different data, all the images in the world, right? Took that whole set. This one should be maximized. We maximize that. All the features associated with the same image. Doesn't matter is the teacher, student, the slow one, the fast one, or from different crops, augmented one. They all should be similar. Okay, this is the contractive part. Right? In fact, if you know the coding rate, right, you don't have to use a Euclidean norm. You can just unit them together, minimize the volume. Okay, which is actually equivalent. 你要下去自己做一做这个 slide up to first order. Actually, they're equivalent. Compute L2 norms or unit them together, minimize the log determinant, okay, of all the vectors. They're actually equivalent up to first order or second order, right? So exactly the same measure, very much. Then for the whole set, you want to be maximized. You want them to be large. This is exactly the concept of rate reduction, 对不对? Or similar should be compressed, grouped together, minimize the volume. What's different, or the union of all subjects, all images featured should be the whole sets should be maximized. The volume should be maximized. Then you put them together, what's similar should be similar. What's different, the whole set, the whole. This is the parts, this is a whole, right? Maximize the whole, minimize the parts. That's it. All right. And also, even here, there's a different variants you can play. Okay, as long as you know what this is doing, right? L2 norm, coding rate, rate distortion, doesn't really matter. Volume, doesn't really matter. You can play with it. Just in the practice, the reason we picked this one, in fact, remember in the closed loop system, in the end, in the final representation, we actually use the distance, L2 norm, because it's easier to compute. Okay, conceptually, it's doing the same thing as minimizing coding rate here for the same group. So you actually get the. So actually minimize this. Remember, there's a negative sign, right? Minimize the negative of this is actually equivalent to maximize this. Okay. So this is exactly conceptually the coding rate reduction. Remember? But you do this for massive, a lot of images without labels. Okay? This is per image. This is for all the images. Of course, in reality, in practice, you do this for huge batch. Okay? You do this for a huge batch. Hundreds of images Here, there are all the features should be expanded. Here, each image you consider as one class, right? Or the augmented consider as one class, okay? Do contrastive learning, contractive learning, okay? This is a contrastive learning, this is a contractive learning, okay? And all measured by the same thing. And once you do this, this is a new pipeline called a simplified Dino. The object function is like this. All right, object function become very simple. I don't want to tell you, the time is not enough for me to explain what the loss function for the Dino is. You can go to find it out, okay? Read the papers to find out what is a cost function for Dino, right? And this is, of course, after a couple of years, the empirical success of Dino, actually, the team come up with the Dino version 2. This is the new diagram, right? Anyway, I don't know how they came up with all this, but anyway. And this is actually Dino version 2. You can do, using the ideas, you can simplify, right? All the things unnecessary pipelines gone. And the object function can become extremely simple, okay? Clean. And conceptually simple and computational easy, efficient, right? And by the way, the training is easy. Not only the diagram system becomes simple, training, actually the performance is better than the Dino, both Dino 1 and 2. And also, right, this is one-shot segmentation. This is on classification on ImageNet. This is on segmentation, image segmentation. They're all actually some of them actually improved quite significantly, right, compared to Dino. And again, semantic segmentation on different data sets, videos, and all actually seems to improve consistently. Some of you can see actually improve quite a bit. And also the training is much more stable, right? In the past, right, if you train the Dino, people have to stop somewhere, right? You have to do early stopping. Otherwise, if you keep training, actually the model tends to collapse. Okay, the performance actually degrade if you keep training. Turns out for Dino, it never happened. Right? It just continually very stable. The performance will continue. The more you train, the performance actually still remains increasing or stabilizes. It's kind of very interesting, right? And also you can see this is a behavior, right? And also it's much faster to train, right? You can see the performance, the KM on ImageNet 1K actually improve very, very quickly compared to different things. So this is the benefits you see once you be able to simplify things, right? Do things correctly, both the object function and also the architecture. You actually understanding what you're doing allows you to simplify dramatically, right? And also gain performance, gain benefits of it, right? So this is a segmentation. Actually, I heard that right now Meta and Google are getting simplified Dino now. They're engineering that now. They're no longer using the old architecture, right? And you can see that from Dino and Dino, actually not only performance similar, right, but it's much simpler, right? Arguably, sometimes it's even better. Okay, now, so that's actually give you one taste. A taste of, even you are just doing one piece, right? In the past, there's massive engineering just doing this one piece of, 对吧？大家都是盲人摸象，摸了一个 leg, and try to scale it up for billions of images. Okay, that's actually what people really doing these days, right? And then claim that's everything, right? It's kind of very toxic mindset, to be honest, right? So this is one example to show you, right? If you understand what you're doing, you can dramatically simplify. Even for one piece, the practice of one simple piece, you actually can do much, much simpler, much, much better, right? Now, and also, we wanted to know, right, how to do this, giving us new architectures, right? Completely explainable architectures, right? Remember, we have gone through this before, right? If we know our representation is trying to learn such compact structure feature, then we have the object function. This through unrolled optimization, we actually can know what this transformation really is, right? We can go through this very, very quickly, right? And of course, in chapter 7, we talked about this before, right? This is a great architecture, but chapter 7 give you the details of how to implement them correctly, okay? how to prepare the features, how to design the architecture, all the implementation detail you can find in chapter 7, right? So this is just try to conceptually, right? Before people design transformers, but now we know what the transformer is really trying to do in terms of repetition learning. We try to realize this kind of deformation, right? Maximize rate reduction, maximize information gain, right? Hence, we can derive this architecture through on-road optimization. Right? For example, we can actually write out from this object function, we can through the unrolling, right? It's just a matter of how do we optimize this, right? We first do, for example, we first do compression, and then to do the expansion specification. Right? So this is exactly very similar, conceptually it's very similar to what the Dino is doing, right? Things should expand, things should contract. Okay. Once I have the expression of this object function, I can derive the operator. The computer gradient, that gave me the operator. Give me the architecture, what it looks like, right? I do this one step at a time. I can compute the gradient, find out what the operator looks like. Well, it's a little bit messy, but you can work it out, right? It's just a mixture of Gaussian, mixture of subspaces. We try to do the denoiser. This is exactly the denoising, right? We try to denoise against the piecewise Gaussian, piecewise subspace, linear subspaces, right? Those are what operator looks like. And they actually looks like the crate, right? Looks like a transformer. We call it multi-head subspace self-attention, right? Let's just have this expression. Remember, we have multiple ways of deriving this, right? You can do the rate reduction, do a Taylor expansion. You get similar things, okay? For similar groups, or you directly fit the subspace, mixture of subspaces, you get similar operators. All right. And once you do the this is a compression part, right? This part is about I'm doing denoising. This part is doing this actually. Shoot, just waiting a long time to find the big picture. This part is exactly in those errors. We're doing denoising against the those red errors. We're trying to get rid of this nonlinearity as noise. Okay, we're projecting them onto subspaces. Linearize that part. Right. So when you denoise against a mixture of Gaussians, mixture of subspaces, you get this form. Right. And also then the next thing is you want to separate. Right. You want to expand different parts, different lines, different subspace up to different part. So you want to sparsify them. You want to make the subspace align with the axis, make them sparse, right? Make them orthogonal, make them sparse, right? That's the second step is doing, right? Then you use the ISTA to, again, you use optimization to move your features, rotate your feature, make them sparse, make it expand. Right? Then you get this two term, right? Compression and expansion, right? Sparsification, compression, sparsification, right? You alternate, you get this kind of network architecture, right? To compare with crate, right? So compare with this is sort of white box. Compare with what really the transformer, right, is doing, right? This is multi-head. This is the multiple subspace self-attention. This is a multi-head self-attention. The forms are very similar, and here you place with MLP with actually ISTA block. So you actually can learn. For example, now once you have this architecture, right? Chapter 7 has the details. You can train on, for example, EBZ. If you have a data, right, with a classifier, you can train output of the network, do some linear weight, and try to do classifier, right, to predict the classifier. And that's a cross entropy. But if you have, this is actually for the classification algorithm, right? You have a data classification using a feature f theta to do a linear classifier, to learn a linear classifier, right? And that actually works. Can see that, this is interesting, right? So you can see the report. Turns out, remember the crate feature, the crate architecture precisely trying to sparsify the features, right? To orthogonize the subspace and also sparsify. As you can see, indeed, indeed, the feature gets more sparse. This is a layer going deeper and deeper, right? More layer, the feature gets more and more sparse. You can see from here as well. And also that the compression term, the thin parts, the coding rate also is dropping. So basically, this is on the entire data sets of ImageNet, right? Feature spaces. The coding rate drops each layer by layer. And you can see that right now, this is kind of comparison. This is a while ago. We never really quite engineered this to death, to be honest. Right? At the time, we just engineered this good enough to be getting close to the VIT. Right? This is already 2 or 3 years old results. Right? We trained on the ImageNet with the resource we have. So you can see that with a similar size of object network, you very much get very close to what the typical VIT performs on ImageNet, on other classification data. And in fact, in terms of segmentation, actually we did much better actually. With the feature learned from the crate, the segmentation is actually much better than the VIT, the feature learned from VIT. All right. Keep in mind, the crate is never meant to learn a classifier, right? A lot of the previous, Redo network, a lot of deep network in the beginning, right? They never really explicitly try to learn the feature for the data distribution. They actually just try to learn a feature for the classification task, right? They're highly overfit for that task. The feature actually learned is actually not very good representation. It's not very good representation for the data, the X part, right? We actually saw that before. Right? So this is still one way, right? By the way, this is still learning from X to Z, right? Open-ended, open loop, F to Z, right? We use that for classification, right? So far. But we talked about this before, right? Very often we do want to decode. We do want to, the learned feature, we want our representation to be consistent. Still be able to decode the original X to some extent, right? We already know what's a good regularizar for Z, right? We know this. Right? Try to promote to be incoherent, linear. We know we know this part. But what about D, right? Well, this part we know, right? Hence we can use, for example, we can still following our crate design, right? If our goal is to learn Z, the RZ try to promote the rate reduction, right? We know what is the encoder should be, right? The F part should be the white box encoder via unrolled optimization for this delta, the rate reduction. This is actually give us a good encoder, right? But what about decoder? What is this process? We know this process, right? This is the encoder. Try to sparsify. Now, of course, conceptually, we want this decoder to be a reversible process, precisely doing something opposite to this. Whatever gets removed by F, we want to add it back, right? So hence make this encoding, decoding somewhat reversible, right? So you want to almost like in diffusion denoising is doing, right? We try to do. So the forward process is convert something noisy or nonlinear to linear incoherent. The reverse will try to give the deformation back. Right. Hence, we actually should be, hence, we have to work out what is the forward process, right? The forward process is actually try to do denoising against those linear subspaces. Maybe the backward, the reverse process, we should add those noise or deformation back to the data. So, for example, right, the forward process, we're trying to denoise, right, get rid of those one. Each data, this is a subspace. Every data, any data has, we do an auto regression. If this part, we remove the error, right, against the subspace. And the reverse part, what we should do? We add this back. Okay? Very simple. What gets abstracted? The residual, we add it back, right? So we call this structured denoise and diffusion, right? So we don't add a random Gaussian noise. At this point, we don't add a random Gaussian noise. We actually add whatever be deducted back to it. Right? We remove structured noise. We also add the structured noise back. Right? So actually we diffuse in a certain way. Right? Hence, you can see, right? When we denoise, right, we remove the error. We go back, we add the error back. Right? Encoder, decoder. Right? All you have to do is flip the sign, right? So hence you can see F top is the encoder, right? Try to compress, linearize, all right? Bottom is going this way, right? So here is sum, here is minus. Very simple, right? So once you understand, see, this is why this becomes so clear is that once you understand what the encoder is doing, then what the decoder should be doing is also become transparent, right? You want them to be reversible of each other. Right? This add the noise, this. And also decoder is actually easier because see, when Z equal to E as Z, right? When we try to solve this part, the reverse part is hard, right? You have to solve E star. But the forward part is easy. Once you know the dictionary, this mapping is easy, right? There's one side is very easy, especially if you have a linear dictionary, right? One side is very easy. Y equal to AX, from X to Y is very easy. Y to X, you have to solve the inverse problem, okay? So, but you know exactly what it is, right? This is just to give you the algorithm. Solve the inverse algorithm. You call the star algorithm to solve the inverse problem. Right? Again, right? So both processes are exactly conceptually reverse of each other. At least that's the basic form of those networks. Right? So you actually end up with what F looks like, what G looks like. You get an encoder decoder network, right? We call it create autoencoder operational, right? This is completely transparent, right? And also, what about the distance? Remember, right? Remember last time we talked about, right? Very often we don't have to measure XX hat is usually very difficult, especially in the 3D cases. But the images were okay. So in settings for data such as images, we are actually usually be able to compute the predicted what is the X should tells us the recovered X and the ground truth X. We actually can create from data. We can do so-called the self-supervised learning. Right? We'll show you how to do it, at least for images. Right? How do we set up this? Right? We want a Z. First of all, remember this is our autoencoding. We want Z to be structured. Also, we want Z to be at least preserving information to the point we'll be able to recover X. Very similar to X hat. X hat will be very similar to X, right? We wanted this training to be not supervised, but actually unsupervised, for example. I don't want to label all the images, right? From class, like the image network thing. That's very expensive to do. We just want to use the images themselves to do unsupervised learning. This is the purpose number one. Purpose number two, I do want the training loss, right? To enforce and explore the low dimensional structure of the distribution. What does that mean? For example, if I want the X and X hat to be the same, right? The easiest, if I just the superposition is just X and X hat is the same. I mean, then the easiest is just I learn identity map. I don't do anything. I don't do any compression. X equal to Z, Z equal to X. That'll be simple, right? So this is another trivial encoding, decoding. Okay, just like the contrastive learning, right? Every feature mapped to the same point, collapse, right? Here, autoencoding just become identity map. If you just do X minus X hat, you want X hat to be exactly as X. What do you really want? What is the loss? You can first really be able to show that you have learned the low dimensional structure of Z, of this distribution. Remember, X natural image has a very interesting low dimensional structure, right? How can you make sure Z has learned that structure. Learn something rather comprehensive, something compressed. Doesn't keep the data as it is, right? So you kind of want to force this process to be compressive, at least intrinsically. If you learned one thing, remember, since this guy has very low dimensional structure, lies on surface with very low dimensional structure, hence, I don't need all the picture to recover X. I should be able to only use a fraction. Even I see a part of the image, I should be able to recover it. Remember that picture, right? Last lecture, we did this conditional generation. If I have learned the distribution of the data, I only need a very small fraction. I only need to see a fraction of the image, should be able to pin down, find the intersection of that surface and the observation, right? Remember last time? Right? Solve this. And also X, remember X satisfy some low dimensional structure. So to explore this one, if you get this one correct, right, you only needed to see a very small fraction of X, be able to recover, generate X properly, right? 还记得吗? Still remember? We talk about this. That's exactly Bayesian. You should be able to use it. Hence, here, to make sure, right, this process has learned the structure, low dimensional structure of this X correctly, you should be able to recover X hat from very small fraction of X. You can use this fact to see if the learning is good or not. In fact, we actually have in signal processing, people have been doing this forever, right? We are using linear structure. Only that the distribution we have using the low dimension. If some data has low dimensional structure, like a PCA or subspaces, or the matrix has all low rank. If a matrix has low rank, turns out you can complete it. If the data rows and columns are highly correlated, okay? Only you see a fraction of it. You should be able to complete what the number looks like. 是不是? So we have been doing this. 哎，大家知道这个问题有多重要吗？这 completing matrix completion, right? 大家知不知道这个问题有多重要啊？有多值钱啊？对吧？这就是 page rank， 这就是。整个 Google search engine， 整个 Internet 靠这个赚钱，没有夸张啊。TikTok 所有的推荐算法靠这个赚钱，就是靠这个。OK correlation， 哎，淘宝怎么推送给你要的东西，对吧？为什么知道我老婆喜欢这个小那个，对吧 ？Why they know what I like, right? Because I have ranked movies, videos. You have watched how much time. This may not be your ranking, but it's how much time you spend on each type of videos. Or how much products you buy. Other products. So you don't buy everything, right? But based on what you have bought and the correlation between those products and your preferences, you can guess. Then they can recommend those things to you. Even if you have never seen this movie, have never bought this product before, they can guess what your preference looks like. PageRank is exactly doing this. TikTok's doing this, right? Douyin is doing this, right? Taobao is doing this, right? Netflix is doing this. Everybody is doing this. Okay, it relies on this problem to make money. 对吧？这是不同的推荐算法。At the core, just do this. Right? Why? Because our preferences are correlated. 对吧？ 男人跟男人，女人跟女人，对吧？中国人跟中国人，日本人跟日本人，就是 a different culture, different religion, right? Different geographics, different you grow up, different economic class. So people are clustered. We don't have 我们这个世界上不是有71种不同的人，对不对？ Our preferences are all random, right? People with similar background, similar economic background, similar culture, right? We have similar taste, right? They can leverage those correlations. Right? This is matrix completion, right? They're precisely leverage that data like this. Intrinsic degree of freedom is very low, highly correlated. They're not a full rank, not a random matrix. Okay? 就跟图像自然图像是一样的 just like natural images. The distribution is not random, right? Satisfy fx equal to 0. Okay? Right? So highly strict x has to be on some very extremely low dimensional surface. Except this is a little bit simpler, right? This is those structures linear. But this one may be some weird shape, right? That's why we want to linearize it, right? No, but of course, natural image is not linear, right? Not like a low rank matrix, right? Is it not linear? What do we do? But still, since I know intrinsically those images are lying on very low dimensions, hence I only see a fraction of the pixel. I should be able to, if I get f of x right, okay? If I have a good hold of fx, I should be able to do this. Half of the pixel, for example, 对不对？50%甚至一半，一小半的 pixel, I should be able to recover it. Okay, hence the idea of called mask-auto encoding, right? 凯明的2022年的折腾，对吧？那 if you can learn some encoder, just use a fraction of pixels, right? Or patches here. In the case, it's just I say a fraction of patches, almost like I include something. I should be able to match the feature space. Then that should find where that surface is. Right? This is f of x0, right? So a very fraction of pixels. Right? This is y equal to a of x, right? So I see fraction. I should be able to pin down where it is, where that in that feature space. Then I can decode back to get a full image, what it looks like. I have the full information. What is the full picture? Agree with a fraction of those patches. 明白吗? This is a very simple concept. OK? 明白吗？就在做，就是如果你学对了，对吧 ？Feature space 做得对。You can conduct very effective Bayes inference, conditioned generation, condition recovery. Right? The only difference is that, well, he doesn't know what the heck the decoder is. I mean, he try, okay? If you have a few thousand GPUs, you can try, okay? Try different architecture, try encoder, decoder. I mean, in Kaimin's case, they're not even symmetric, okay? He doesn't even quite know what the heck this guy is doing. Maybe some compression, some heuristic, right? Also, sometimes relies on something already pre-trained. Start with something warmed up, some encoder, maybe, train on ImageNet through some classifier. Okay, take some few layers. And then do a decoder. Okay, decoder, we don't know what it is. Okay, let's try some maybe, transformer and so on, right? To do upsampling and so on, right? People borrow some decoder from, upsampling, whatever, right? Decoder, deconvolution, right? You can try, right? Somehow, I heard that he actually spent a lot of compute, right? Learn such a model, right? Learn this representation. Do this. No, actually you don't, right? Now actually you don't have to guess what it looks like, right? So here you already know that this one is supposed to do this kind of, you want this to be promoted as piecewise linear, right? You know what the operator should be doing, right? Do denoising, do linearization, or do contrasting. Supposed to maximize something like a rate reduction. And also decoder should look like this, right? So now for you should be just exercise now. 所以这就是对吧？ 目标很清楚. When you have a very clear objective, what you're supposed to do, the rest is easy, right? You don't have to guess. You don't have to try, okay? You don't have to waste a lot of resources to rediscover things from scratch. Hope some generic network, right? Hope some generic encoder-decoder has the capacity to somehow converge to structure like this, okay? That's what people have been doing, right? You start with some generic, maybe close enough. Hopefully using a lot of data, a lot of it, then gradually maybe converge to operator something looks like this, right? No, you don't. You know this has to be of this form. All you have to do, the architecture is this, right? All you have to do is just learn those parameters. That's all you have to do. Right? Then you can train this. This is actually what we call the create MAE, right? Everything's transparent. Even the operator is transparent. What it does, geometrically, statistically, is exactly doing this. 你可以把它画出来，它每一层算子在干什么，对不对？它对数据在做什么处理 ？Geometrically, statistically, remove the error, residual, add back the residual. OK? 这个在干什么？我不知道啊。But somehow it works, right? But in the end, yeah, so you can see this is actually this is VIT, right? This is 凯明在这弄的，对吧？折腾的啊。Visual transformer. This is actually our create VAE. You can see that actually very much the same. In fact, in many cases, actually we're better, right? So you can see in terms of classification, we're getting very, very close, right? Similar feature learning. And in fact, in terms of segmentation, we're actually much better, right? Because those feature spaces, really help with getting the contrastive different classes of objects. Really, the features getting differently, right? It's very discriminative. The feature space we learned, reproduction, you actually get a very, very good linear subspace structures and from the features. It's good for classification, good for visualization, and so on. Again, think about it's just like a Sindano, right? Again, you can already explain. First of all, see, you can with the concept, you can already explain what other people try to do, even they are not sure, even they don't know what they want. Okay. That's actually the reality. A lot of people that are doing with AI, they train us, they don't know what they want. They don't know what they're doing. But maybe they really want some downstream task to become better. Okay, they turn a lot of resources, try a lot of ideas. Hopefully the downstream classification, downstream segmentation gets better. But in terms of feature representation, they don't know what they have done. Okay, in terms of encoder and decoder, they do all kinds of regularization to avoid collapsing or try to make sure that the feature learned somehow helps with downstream task, can improve a little bit. That's kind of the practice, right? But now you don't, right? Now you know what they should be doing. Hence, right, the object function can be very clean. You don't have to guess the object function. Second, once you know the objective, the architecture to optimize it also become clean, completely transparent, right? You only have to change a little bit things, right? Clear? All right, this is a time to maybe take a break. Also, in case you have some questions, this will give you example, two examples already see, right? Once you know the concept, once you know the principle from this course, you should have a much better understanding of the current practice. Second, you should be replace some of the existing practice with something completely fully explainable, completely transparent, right? And you don't have to guess a lot of the choice of architecture, choice of operators, right? So on, right? So you can focus on other problems that really deserves your attention, right? You can optimize the systems better. So, okay, let's take a 5 minutes bio break. And also in case any of you have questions, what time is it? That one is a little bit off. 3:17, we can maybe 25. How about we take about 8 minutes break? Right? We resume at 3:25.